series on, can't I? Okay, so let's try this. This one, well, let me rewrite this. This is going to be 1 over, well, yeah, see, that's a problem because this is backwards from what it is over there, right? So I'm just going to put the negative on top. Put a negative on top, right? So the negative, basically factor a negative out and then move it on top. And then switch the order. And then on this one, minus, I'll just rewrite it first backwards. So negative 1 times 1 over 1 minus x minus 1, minus 1 over 1 minus 2x. Do y'all agree with that? Rewrite that one like that. This one is almost what it needs to be, right? Just changing the plus to minus minus. Louise, you all right? Okay. All right. You just have this like dazed, like this look of, maybe it's astonishment. Okay. Negative 1 times sum n equals 0 to infinity of x to the n. That's this. That's just a formula, right? This is only going to work, right? This only works when? If the absolute value of x is less than 1, okay? Now here, this one is going to become sum n equals 0 to infinity of negative 2x, right, to the n. So I'm going to put negative 2 to the n, x to the n, splitting it up. And that's only valid when? When the absolute value of, I'll do it this way, is less than 1, right? So this one's only valid when the absolute value of x is less than 1. This one's only valid when the absolute value of negative 2x is less than 1. But that's the same, this one is the same as what? Saying what? Absolute value of x less than a half. So what's going to be our restriction then? 1/2, because it's got to be working for both. So this is going to be, this is only valid on this, okay? The smaller of the two intervals. All right? I think we have rewritten this, right, as a power series. No, we haven't. It's 2 power series. We need it as 1 power series. So what we're going to do is try and put these two together.
Distribute the negative again, and then just like 1 minus, or 1 plus 2. Thinking outside the box.
Are we allowed to? So can I pull this negative 2 out of this? It has an n, so no. Do we want to write each one of them out? So the question becomes, what can you do and what can you not do, right? In terms of these power series. So let me rewrite it this way. Okay. So see if this would make sense to you, that we can now say this. Does that make sense that that would be the same thing? Because this says what? Add all these guys up. And then this one says add all these guys up. This says add them up at the same time. So like you're doing these and these, right? You're doing them both together. So you're covering what these two sums do. But all I did was took this and put those together in a parentheses, right? And separate them by this sign. Follow? Now they both have x to the n. Right? They both have x to the n, so I'm going to factor it out. So my next line will be, I'll leave that up there. Next line will be sum n equals 0 to infinity. Okay, I'm going to write -1 minus -2 to the n times x to the n. So all I did was I pulled the x to the n out, factored it out, but I pulled it out to the back instead of the front, so that it would look more like a power series. So when I pulled this out, I left the -1 here. When I pulled this out, I left the minus -2 to the n. Do y'all see that? That's it. We're there. Yeah. Is this not a C sub n? It is, right? It's not pretty, but it is what it is, right? And then this is our x minus a to the n. So we're done. We could write a few of these out, couldn't we? I think we'll stop now writing them out. But we could, right? Okay. All right, moving on. We're almost done with this. And we can move on to the next section. Yeah. This is our last example. Save the best for last, though. The 2 stars up in the left corner mean that this is extremely fun. Okay, that's what 1 star is, it's fun. 2 stars is extremely fun. Okay. You want to just factor the whole top out? Is that what you're saying? No? Oh, you could pull an x out? Or take derivatives?
You could set it up to find out what the integral of, like find the derivative so you know what the integral is.
Yeah, like maybe this is the derivative of something or an integral of something or.
Yeah.
But the only thing we have to work with is this, right? That's the only thing that we have to work with. It sucks that we only have that, right? In the next section, we will be freed from these chains, all right? So, okay, so maybe we just look at this for a second. Maybe we look at 1 over 1 minus x cubed. What if we just had that? What if that's all we had? That's the derivative, that's like second derivative maybe of something? Maybe. Maybe. So let's go back. When we looked at 1 over 1 minus x, what was the derivative of that? That was 1 over 1 minus x squared, right? Agreed? Okay. What's the derivative of this? What's the derivative of 1 minus x squared? Now be real careful here, because it's not 1 over 1 minus x cubed. So that's the same as taking the derivative of 1 minus x to the -2, right? So take derivative of that, what do we get? -2, 1 minus x to the -3 times -1, which just gives us a +2 over minus x cubed. So this is a 2 here, right? That doesn't have a 2. That's okay. So let's see. We realize now that this is actually half of that, right? Because that would kill the 2 out. So this is half of the second derivative of 1 over 1 minus x, right? The derivative of 1 over 1 minus x is this. The derivative of that is this. That's off by 2, right? So half of this is, okay. So this is half of the second derivative of that. Second derivative of that. What's that? What do you mean? No, because look, this right here, right? This is the second derivative, right? It's the second derivative of that. So that was the first derivative. We took derivative of that again and got this. That almost matched this, except the 2. So I can't say that these two are equal. I can say that this is half of that, right? All right, so big deal.
So you're saying the next line after that is the third derivative of it?
What next?
Just the next, never mind.
No. This is the second derivative. This is the second derivative. Okay, back to this. Let's see if we can't make this work. Do you agree with that? Okay, so I have this. I can put this over this plus this over that. So separate it into 2, and then pop the x squared and the x's out. Yes? All right, now we need to figure out how we can rewrite this as a power series, right? If we can get those to be power series, we'll be in business. But 1 over 1 minus x, that quantity cubed, is half of the second derivative of that, right? So what are we going to do? So we're going to be taking the power series for this and taking its derivative twice and then doing half of it. And that's what will replace that expression over there. Okay? So I need to do some more scratch work on the side here. Let me go and work with this. So here's what I'm going to work with right here. 1 over 1 minus x, that quantity cubed, equals half. Okay, let's just replace this. What's this right here? This. Sum n equals 0 to infinity of x to the n, right? But we need to take the derivative of that twice. Wait a minute, didn't we already take the derivative of this earlier? We did, right? So let me do this. Okay, so I'm going to write it this way, so maybe it makes a little more sense. We're going to be taking derivative twice, right? So I'm going to take this series, I'm going to take its derivative, and then after I'm done with that, I'm going to take its derivative again. But this piece right here, we did in a previous problem, didn't we? Okay, so what did we get as our final answer for that power series when we put the n back to 0? Because we did put the n back to 0, didn't we? So it was 1/2, and then I'm going to have sum n equals 0 to infinity, n plus 1, x to the n. That was the derivative of that power series, and now we need to take the derivative of that again. And I'm running out of room. So that should be equal to 1/2. Okay, let's take the derivative of this power series right here. So this n plus 1 is our c sub n, so it doesn't get touched. But I do power rule on this, don't I? So what happens? N comes out, and we subtract 1, and the index goes to 1. So we have 1/2 sum n equals 1 to infinity of n times n plus 1 times x to the n minus 1. So the n came out, left this alone, x to the n minus 1. Index came up. Let's get that index to be 0 again on the bottom. Can we do that? I mean, we're there pretty much. We have a power series. But let's make that n 0. 1/2 sum. If I'm going to make this n 0, right? If I'm going to make that n 0, what do I have to replace n with? N plus 1. If I replace that with n plus 1, it becomes n plus 1 equals 1, and you subtract 1 from both sides. So I'm replacing, from this line to this line, I'm replacing all n's with n plus 1. So we get n plus 1 equals 1. That gives us n is 0 to infinity. That gets replaced with n plus 1. That n right there gets replaced with n plus 1, so it's n plus 1, which is going to be n plus 2. And then that's x to the n plus 1 minus 1 is x to the n. Bam, there it is. Yes?
I don't get how you made n equal to 1 and n equal to 0 by adding 1.
Okay, I'm replacing this n right here with n plus 1. So this line now reads n plus 1 equals 1, and then I subtract 1 on both sides. Thank you for asking, Chris, because I know people are confused on that. But, I mean, it's important that you see that. If you were to replace n with n minus 1, then this would be n minus 1 equals 1, and that would become n equals 2. And that's not what we want. All right? Are we good? Is this a good power series? Starts at 0, x to the n. We're all good? Okay, we're not done, right? Because this is what we're trying to rewrite. Y'all ready for me to rewrite that? Okay, so now we go back to this. I'm going to keep this handy because I'm about to use it. This now becomes x squared times 1/2 sum n equals 0 to infinity of n plus 1 times n plus 2 times x to the n. Okay, that's that. Plus this one, x times 1/2 sum n equals 0 to infinity of n plus 1 times n plus 2 times x to the n. Have we rewritten this as a power series? Almost. It's a sum of two power series. We got to get those two together, right? But we've got x's out front, don't we? See the x's out front? X squared, x. Let's push those in. Push the x's in. 1/2 sum n equals 0 to infinity of n plus 1 times n plus 2 times x to what power? N plus 2. Okay? Plus 1/2 sum n equals 0 to infinity n plus 1 times n plus 2. Is this math hell? This is math heaven. This is math heaven right here. So I was sitting down with one of my former students. We keep in touch. He comes in and visits my office every once in a while. He's a math major. He's about to graduate. He's going to get, I forget what his degree is, but he's taken quite a few math classes. And he sat down with me when he was in Cal 2, and he was like, I'm a math major. And I said, are you sure? You sure you want to do that? And, okay, so the reason why is, and this is what we were talking about, I tried to explain to him back in Cal 2 and 3, like, math is not what you think it is. Like, if you go on and get a degree in math, it is not what you think math is right now at this point of Cal 2 and Cal 3. It's totally different than what you think it is. So I tried explaining that to him. Then he was sitting down in my office yesterday, and I was talking to him. And he was like, yeah, you're right. And I said, but how do you explain that to somebody? Like, he's like, yeah, you can't really explain it. It's hard to explain. This right here is nice. Like, this is like This is mechanical. It's very mechanical. It's, there's a lot of little things that you have to remember, but this is not like theoretical math, which is completely different, which is what math majors have to get into, theorem proving, things like that. So if you are a math major, you should sit down and have a discussion with me or somebody who's gone through it so you have a real idea of what it is you're doing. Because if you're attracted to math because of this sort of thing, and it turns into something else later, and it's kind of like, ooh, So I'm not saying it's bad, because as a student, this stuff I was okay with, like I did all right. Did well in Cal 2, Cal 3 was Once I got to the theorem proving courses, I loved it. And I had friends who really liked this, that they got to the theorem proving courses and they hated it and just quit. So a lot of it depends on you, and I don't even know why I'm mentioning this right now. Oh, this is math heaven, right? It's math heaven. To me, this is not math heaven. Math heaven is proving theorems, but yeah, this is a little bit tedious.
I apologize, but where did you get the n plus 2 on the x over there? I'm serious.
No, I should just shut up, shouldn't I? N plus 2 came from the fact that I pushed this x squared in, and so it raised the exponent. You're like, shut up, just finish the problem.
No.
Yes, no, it's all right. What's up?
Proving theorems, like, as in just proving fundamental theorems of like calculus?
Well, okay, so like in math majors, they have to go back and go through all of the algebra. I mean, you have to start with like the number system, like simple stuff, like why is a plus b equal to b plus a? Like, I know that seems stupid, right? But you have to prove it. Like, everything has to be proven. And then, there aren't many open questions in math. Like, you're not going to be proving your own theorem, like creating your own theorem and proving it, unless you're going to go get a PhD. In fact, that's what qualifies you for a PhD in math, is you have to have what's called original thought. It has to be original thought. And that's hard with a subject that's thousands of years old. I always equate it to like a tree. You have the trunk, right? We're still in the trunk, okay? Calculus and all that. And then it starts to branch off. Like, I know we're off topic. Most people, even myself as a student, thought math was very linear. Like, you just start, algebra, pre-cal, Cal 1, Cal 2, Cal 3, and you just continue down this road, just one class after the next. But it's not like that. Once you get to Cal 2, after this, it starts to branch out. So now you can take more than one math class at a time. So you can take linear algebra, differential equations. You can take modern algebra, topology, number theory. I mean, now it starts to branch out. So you've got all these branches, and then down each branch, there's smaller branches, and then smaller branches, and eventually you get down to, a single leaf on the tree. And that's the open questions. All right, those are the things where getting to a leaf usually takes 8 years of study. It's like being a doctor. You have to go and spend 4 years undergrad and then 4 years. It's like even getting to a question is hard enough. Then answering it is the other thing. So you can have two math. This is what I didn't realize as a student. Let's say I had a PhD in math, and you had a PhD in math, and you had a PhD in math. The chances that you too would understand my work it's probably not. Like, you would read my work and you'd be like, what the fuck? I'd read yours and be like, what the fuck? Like, it's so specialized. Does that make sense? You ever heard of Fermat's last theorem? It was proven a few years ago. And the first time it was proven, there were only like 3 people in the world that understood the proof, because those people had been working together. So it took more time for others to come in and understand it and understand the ideas, have to build up that they had to go down that branch, okay? So, yeah.
That conversation here, I proved it.
Yeah.
Proved it.
Yeah. But so like in like an undergraduate math, students have to develop all the skills in theorem proving. Like, how do you even prove something is true or not? Right? Like when can we sit there and say, yes, you've shown what you need to show, and you need to understand that. And so that's what a math major does. It's really logic. And that's why computer scientists and math, like once you get into graduate level, computer scientists and mathematicians are almost one and the same, because it's all logic. Okay, I'm going to shut up now. I'm going to finish this problem because it's really nice what we still need to do.
Combine them. We can only have one power series. Right?
Yeah, we can only have one power series. And do y'all see a problem that we're going to run into? The half? Do you remember in the previous problem we put the power series together? And then what did we do? We factored out an x to the n.
And x to the powers are different.
Yeah, so see here how we have different powers? That's going to be a problem because even though we can factor out a common factor, which would be x to the n plus 1, we would be leaving an x still in the other part that's supposed to be the c sub n. Does that make sense to you? Maybe I write it down real quick. Let me write it down. 1/2 sum n equals 0 to infinity. Let's say I put this together with this, okay? So if I put that in there, I'm going to get n plus 1 times n plus 2, x to the n plus 2, and then plus n plus 1 times n plus 2, x to the n plus 1. Okay, that's both of those put together, right? But see, from here and here, I can only pull out an x to the n plus 1, which means what's left in here still has an x in it. Do y'all see that? And c sub n can't have x in it. So what we're going to do here is we're going to make the exponents match. Okay? I'm either going to make them both n plus 2 or both n plus 1. And I'm just going to choose right now to do n plus 2. So how would I make this an n plus 2? I'd have to replace n with n plus 1. Okay? So let me do that. And I'm only doing it on that one, right? Okay, so if I replace n with n plus 2, so just on this one, not n with n plus 1, then my new line here becomes this one, 1/2 sum n equals 0 to infinity, n plus 1 times n plus 2, x to the n plus 2, plus 1/2 sum n equals 0 to infinity. No, not 0, but n equals, I'm replacing this n with n plus 1, right? So that's going to be, n equals -1, right? Okay, what about this one? I'm replacing n with n plus 1, so n plus 2, n plus 3, and then x to the n plus 2. Do y'all agree with that? It's ugly, but it's what it is, right? Okay, now could we put the two together because they have the same powers? They have different indexes now. This one starts here and this one starts here. What's that? Okay, so this is how we get around this. You can't go and switch these both back to the same thing or you're going to have the same problem, aren't you? So it might help if you realize that, let's see, this one starts at n equals 0, this one starts at n equals -1. It would be nice if this started at n equals 0, wouldn't it? So I'm going to write it this way, plus 1/2. Let's go ahead and plug in -1. What would happen if we plug in -1 here? We get 1 times 2 x to the first power, right? Now we've plugged in -1. The next thing we would do is plug in 0 and then continue, right? So instead of me writing, like the next one, I'm going to write now my sum goes from 0 to infinity, n plus 2, n plus 3, x to the n plus 2. So essentially what we've done is taken this and peeled off the first term of it, right? Just the first term. and then rewrote the rest of the terms as the sum. That seem valid? And then out here we still have this one. And now what we can do is we can put this and this together because they both start at the same place and they both have x to the n plus 1. So this peeling off a term is just a kind of a skill you need to know and be aware of, that you're allowed to do it. Now this piece right here is just going to stay as part of my answer. So what is that? Just x? So I think I'm ready to rewrite this. This is equal to x, that's this, and then plus a half sum n equals 0 to infinity. I'm going to put this together with this, right, with addition between them, and I'm going to pull the x to the n plus 2 out. So we should have n plus 1 times n plus 2 plus n plus 2 times n plus 3 times x to the n plus 2. So that's this one right here. Basically this part here, and then it's this part here put together with addition, because I'm putting them together, and then I'm pulling the x to the n plus 2 out of both of them. And then this, I guess we could clean that up, but I'll just leave it. That's a c sub n, isn't it?
Is that the final answer right there?
Or do you want it in terms of x to the n?
Well, we can leave it like this if we want it to start at 0. Or you could start it, you could go x to the n. Since we're basically running out of time and I don't have enough time to start a new problem, let's go ahead and just make it x to the n. So it looks like this, okay? So what would I need to do to make that x to the n? I replace n with n minus 2. So I'm replacing n with n minus 2. So now I have x plus a half sum n equals what? Replacing that with n minus 2, adding 2 to both sides, 2 to infinity. All right. Replace n with n minus 2. N minus 1. Okay, here. N plus n plus 1. Okay, all of that x to the n. Okay. And now we can even clean this up because algebraically it does clean up. If you pull an n out of both of these, and then you'll have n minus 1 plus n plus 1, like that. And that turns out to be just 2n. So you wind up with 2n squared x to the n sum n equals 2 to infinity. 1/2 out front. Oh, that 1/2 and 2 cancel. Okay, do y'all see what I did here? I pulled an n out. But you could actually just distribute these and then combine them. You should get 2n squared. There's something else I can do.
Can you make it n equals 1?
Yes. Yes. So it's just, this problem works out just particularly good. This and this are gone, right? So now we have this, x plus sum n equals 2 to infinity of n squared x to the n. Okay, that is our power series. That is our power series. But there's one little thing that we could notice, and I'm not sure, Martin, how you noticed it, but this formula, the way it would work, if I start out at 2, right, what would I get first? I get 4x squared, right? Then I go to 3 and I get, I'm going to actually write it out here so you can see it. If I let n be, let's leave this x here, plus it would be 2 goes in, so 4x squared, plus now 3 goes in, so 9x cubed, plus now 4 goes in, so 16x to the 4th, 25x to the 5th, right? So on and so forth. But notice that this one right here follows the pattern. Like this is 2 squared, 2, 3 squared, 3, 4 squared, 4. This is 1 squared, 1, isn't it? And it just so happens that this works this way, that I can actually account for this x within this formula by starting it at 1 instead and getting rid of this.
Can you start at 0 as well? 0 squared?
Yeah, it would be an extra term we don't need, but yeah, it wouldn't hurt it. That's kind of like when I said when you have the derivative, the index comes up to 1. You could leave it at 0. It doesn't affect it. It's just that first term is nothing. So this, after some careful thought, is just this. See? To 1. Because that accounts for that piece. Okay, so that example is just to show you all the little intricacies that can happen within a problem, right? You had to recognize, separate that thing, realize that it was the second derivative of something, right? Take the derivative twice. Oh, you've got to match these indexes up. Kind of messy, yeah? So, enjoy your holiday. Thank you for being here. Did that sign-in sheet get around to everyone? Y'all weren't here then. I don't know where it is. Hold on, let me turn my camera off. Next week, we will prove